So this talk is about the Indus Valley civilization and how and why they adopted the binary system, right? So as I've written in the introduction of the talk, the binary system, if it's not the most important, it's definitely the second most important number system, because all computers use it, right? So we are interested in its origins. So it turns out that this is, this work is pretty new. It's about a decade old, and I was born in Khairpur. Okay, so that's my hometown, and my father was an intellectual. He was a poet. So वहाँ पे जब लोग especially foreign scholars आते थे, so they would often contact my father because he had a huge library in his house and he was interested in many things. He was a doctor by profession, but he was also a poet. So I remember once that there was this Finnish guy. His name is Asko Parpola. Who had come and he had even visited our house, and he was actually working on the Indus Valley civilization and its script. So it's always been, this thing has always been close to my heart. I've been to Mohenjo-daro many times with my friends and spent we used to be kids, so we used to just go and play there and collect pottery pieces and all that. So lovely memories are there for me in Mohenjo-daro. And so what happens is every 3 or 4 years, 5 years ke baad mein, I'll Google Indus Valley script and all that, and what is the new things that are happening in archaeology, especially regarding the Indus Valley civilization. And so I keep doing that every 4 or 5 years and, read a few articles and update myself because it's very close to my heart. So what happened is that I did that again probably a few months back. And what I found was that there were tremendous advances in deciphering the script, and then this fact that they were using the binary system. So I thought about it, and then I think it's related to some subject which is very close to my heart, that's combinatorial optimization. So we will see how it relates to that. So this is Mohenjo-daro, it's an iconic picture. It used to be on our 10 rupee note also at some point. And this is the most majestic of the Indus Valley civilization sites. This is about 4,000 or 5,000 years old, okay? And the Indus Valley civilization is very, very different from all the other great civilizations, okay? Sumerians or Mesopotamians or Egyptians. If you go to Egypt, I mean, the most inspiring things, awe, that will make you awe is the pyramids, right? These huge structures that they built. And, if you go to Rome, they were making huge temples. The Egyptians were making temples and pyramids. These structures which were so large, right? And so majestic that, a human being really looks very small compared to them. And if you really think about those civilizations, they were essentially slave labor. The pharaohs were using the people as slaves to erect these huge structures, right? In the Indus Valley civilization, this is very strange that they don't have any impressive structures. They just have very simple houses, right? But they were extremely organized, okay, and extremely well planned. So, for example, Mohenjo-daro, all the streets cross at 90 degrees. So, you have a planned city, okay? It has underground drainage. Can we move forward here? If so, this is a place which is called the Great Bath. This is probably the most impressive structure that they ever made. Was this Great Bath? It's probably something like a swimming pool where people bathed, maybe communally or maybe for some ceremonial purposes. The cities were planned. They had underground drainage. Okay, and they had wells in their houses. Every house has a well. So imagine yourself that many years ago. You have running water, you have drainage systems, and I mean, it would be wonderful if we could provide that to everybody, even today in this country, right? Many cities don't have proper drainage systems and all that. So these are very interesting people. Now, there are lots of questions about them. So one of the questions is, who were they, right? And there are lots of theories, okay, but the one that is accepted by most archaeologists is that they were Dervedians, right? So the language that they spoke are the languages that were spoken in South India now. Things like Tamil, Kannada, Telugu, those languages. And one of the evidences of that is that if you go to Balochistan, today there is a language which is spoken there which is called Brahvi, right? And that is a Dervedian language, right? It's completely different from the Aryan languages. Actually, Dervedian languages are pretty fun, we find them funny, but pretty nice. If you go to, say, for example, South India, one of the strange things is when they want to say yes, they do this, okay? And it's highly confusing that, you'll be making, you'll be bargaining with a rickshawala and you'll say, 120 rupees, and he'll go like this, and you wouldn't understand that he's actually agreeing with you, all right? So the Indus Valley people had a language, right? And they wrote. So this is a seal from the Indus Valley civilization, and these are their characters, right? Okay, so one of the things is that most of the things that they wrote is lost because they probably wrote on perishable things. It hasn't survived. So what has really survived is seals like this and pottery and things like that. And so Indus Valley script is the last major script which has not been deciphered yet. So in some sense, it's supposed to be the holy grail of people who try to understand ancient languages, all right? And there are many reasons for that. So this is the underground drainage system. So if you go to Mohenjo-daro, you can see what they had is streets, and there was a drain from which I guess water will flow out. And one of the interesting things is it was covered. So there were no open nalas like we have in our cities. So these were people who were extremely, they were very clean, you could say, and very hygienic, right? And so there was one more thing I wanted to say about this. Yeah, so there are people who even claim that the Indus Valley civilization was a democratic civilization. Now, there's no evidence for that. But when you look at their cities, you realize that it was far more egalitarian than say the Egyptian civilizations. For example, there is no trace of any palaces there. So it seemed like everybody more or less lived in similar sized houses. So this is the Indus Valley civilization. This is the span of it. It's from, so I guess you can see Pakistan here. So it's almost all of Pakistan, and then it goes into India, right? Mohenjo-daro is one of the major sites, and I think there are over 1,000 excavated sites of this this civilization. There is a recent discovery. This is Rakhigadi. I think this is in Haryana, and this has been discovered very recently, and it seems like this may be bigger than Mohenjo-daro. All right, they're still excavating it, but the span seems to be bigger than Mohenjo-daro. Of course, you know, you have Harappa and Taxila, right? You know, those are here, and they're really lovely. Okay, right. I wanted to say something about Mohenjo-daro. So Mohenjo-daro is actually, so the question is, where does the word Mohenjo-daro come from, right? And one of the explanation that is given is that it's the mound of the dead, Mohenjo-daro, all right? And that's completely wrong. It has nothing to do with dead and all that, because if you go and look at other sites, there's something like Lakhanjo-daro, okay? And there are lots of daras there, you know, like for example, here we have the Galiyats, right? Nathia Gali, Dunga Gali, this Gali, right? So it's a name of a person and his mound, okay? So it is Mohenjo-daro. It's not, and you know, somehow when Mohenjo-daro was discovered, this alternate explanation that they found skeletons there and therefore they named it this has stuck, and I've read it several places, but that's actually incorrect. It's Mohenjo-daro. Okay, so these are seals, right? And what we want to know is, what are they saying, right? So if you want to understand ancient cultures, what you would be interested, you know, if you can understand their language, then they start speaking to you, right? And we would like to listen to these people. I mean, if I want to understand a culture, then the first thing that I would do is I would want to read their literature, their poetry, their, you know, fairy tales, their, you know, that tells me what kind of people they are, right? So if we can understand them, then we will actually, they will be able to speak to us. But unfortunately, this has not been deciphered, okay? And so here's a, you know, here's a sample of the kind of things they write. This particular series seems to have to do with labor, right? This is, you can imagine a person carrying water and all that. So how do you decipher a language like that you don't know much about? So this is the rebus principle, and the basic idea originally is that suppose you want to write the word belief, and you want to explain this word, or you want to say this word to somebody in pictures, right? And so what you do is you take pictures. So for example, you take a picture of the bee, and then you put a picture of a leaf in front of it. And so the person can, you know, when they say this thing, they'll say, oh, belief, okay? Because belief itself is a very complicated word, you know, it's loaded. You know, it's hard to explain to people what it is, but this would be a way to communicate it. So initially people thought that Indus Valley civilization was doing something similar, all right? And so now we have the backwards problem, right? So you have this, you have these symbols, and you want to find out what it means. Now the problem is we don't even know what language they spoke, all right? And it's very interesting that the Indus Valley seals have been found in Mesopotamia. So these people were trading, you know, with other great civilizations. You find them in Iraq, you find them in Iran, okay? And over there, the writings that you have are very different than the writing that you have in the Indus Valley mainland. Okay, so let me explain to you what I mean by that. So For example, if you look at English, certain kind of characters don't come together, right? So if you have a Q, right, then you always have a U after that, okay? All right, but let's say if you were to, let's say if you were to, okay, so there's an easier example. Nowadays, everybody is sending text messages to each other, and they're writing Urdu in Roman, right? Now, if you statistically analyze Urdu in Roman, it'll be completely different from English, all right? So when you find seals in Iraq or in Iran, which are in the script of Indus Valley, by doing a pattern analysis, they can tell that that's a different language, right? So one of the things is we don't know the language, and we don't even know if it's one language, all right? Now, you saw the span of Indus Valley, you know, how huge that thing was. The estimated population was 5 million people. And that's a lot of people, you know, thousands of years ago. So it was huge, right? So we can't even be sure that they all spoke the same language, right? Because languages do tend to change. I mean, just 25 kilometers away, you have a different language. This is one of the most interesting signs that appears in the Indus Valley civilization. And this was the first article I read about it was actually deciphering this sign, which is this fish sign. And I don't know, it has these things. And initially, Osco Porpola had claimed that he knows what this sign means, right? So fish, the South Indian word for fish is mean, okay? And in South India, mean also stands for star, okay? So he had claimed that this fish sign actually means that it's mean or star, okay? And so there were other seals in which you have this sign, and you have like 6 strokes over there, right? So the claim was that this was a constellation, Pleiades, which has 6 stars or something like that. So this is what they were trying to communicate. All right, but the latest research shows that that's not the case, all right? So I'm going to talk about the fish sign and tell you what it stands for. So let me, with a heavy heart, erase this beautiful artwork. Okay. All right. Okay. So we have a fish sign. Okay. That's the fish sign, and we have many variants of the fish sign. Okay, so for example, one variant is exactly like that, but there's a bar over here. Okay, another one is you have a fish sign, and you know, instead of 2 of these fins, it has 4. Okay, and so on. So there are many variants of the fish sign. So we are going to just call them, let's say, fish 0, fish 1, fish 2, fish 3, and I don't know, some fish K, right? So these are the fish sign. When you start studying, one thing which is spectacular is the fish signs tend to come in clusters, right? So if you have like 3 or 4 fish, or 2 fish, or something like that, okay? So one is they come in clusters. Okay, and the second thing is that the fish sign come, their order is always the same. Okay, so if you have, let's say, if fish 0 comes, right, then you can, after this, you can only have fish 1 or 2 or 3. Okay, so let's say you have fish 2 after this, right? Once you have fish 2, you cannot have fish 1. All right, you will have, so they always maintain their order, right? So these two properties are very mathematical, okay? So the question is what is going on, right? And what's going on is that the fish signs are actually telling you the weight of something, right? So they're telling you a number in binary. All right, that's what's going on. So let me. Is it okay if I tell for the young people what binary is a little bit? Okay, hopefully you won't get bored. Okay, so we do calculation in base 10. Right? So in base 10, we have 10 symbols, 0, 1, 2, 3, 1, 2, 3, up to 9. Okay, there are 10 symbols. We start counting from 0. All right? And what we have is, the way we write a number, say 934, this is units. Okay, this is tens, and this is hundreds, right? And so on. That's how we represent our numbers is in base 10. Now in binary, okay, you have only two symbols, all right? And of course we take them to be 1 and 0 and 1, okay? And instead of units, well, you have units in binary. So here you place your units, and here you place twos, okay? And here you place fours, okay? And here you place eights, okay? So, all right, so in binary, just like in base 10, the places are powers of 10. In binary, the places are powers of 2. Okay, so for example, if you want to, let's say write 11. Okay, so what we do is we realize that 11 is 8 plus 2 plus 1. All right, okay. So I have written 11 as a sum of powers of 2. Now what I do is units, so I have a unit, okay, I have a 2, okay, I don't have a 4, so I put a 0, right? But I have a 8, okay. So this is in base 2 we are writing 11. I'm not writing 1, 1 because that also looks like a binary number. That was not a very good example that I chose. All right. So this is how you write numbers in binary. Now, what's okay? So here, let me write a number in base 10. This is 932. Okay, right? So I could write this as 2 units, right? 3 tens and 9 hundreds. Okay, right? I could write this like this. All right. So in binary, what I could do is here I could write this number. I could write is 1 unit. Okay. 1, 2, okay, and 1, 8. All right, okay, I have no force, right? So what they had was, what the Indus Valley people had was for each one of the units, 2s, 4s, 8s, they had a fish sign. Okay, so there was a fish number 1 here. There was a different kind of a fish here for 2s, and there was a different kind of a fish here for, let me just make it like this, and there was a different kind of a fish here, let's see, right? So if they wanted to write 11, they will write this fish, okay, which is 8, and then they will write this fish, which is 2, and then they will write this fish, which would mean 1. So it will be 8 plus 4 plus 1, which is okay. Yeah, I thought something went. 8 plus 2 plus 1, which is 11. All right. So this explains everything about the fish sign. Why they come in clusters? Well, because it's a number. All right. Why is it that this sign will always come before any of these? Okay, that's pretty obvious. Okay, if you're writing it this way, right? So that really solves the mystery. All right. So sorry about that. Actually, there's a fish sign which goes with each one of them. There was a nice thing telling you. So these are the weights that they were actually measuring. All right, and these guys, these archaeologists are so good that they actually know in terms of grams how much that weight is. All right. So there's one fish which is counting a unit, a half, a quarter, an eighth, a 16th, 2, and then 4, and so on. All right. And then there are larger weights also. All right. So the question is, there is no evidence, and I don't think so that it's possible at all that they were computing with binary. Right? They were not computing with binary. They were just representing weights with binary. Okay. Yeah. Okay. Yeah. So these are different fish signs, and these are the weights. So it's 1/8, 1/4. Okay, this is an odd one, but then 1/2, 1, 2, 4, 8. Okay, then it goes to 14, 20, and so on like that. So can somebody, one of the younger people, tell me why this is happening? Anyone? Why would a culture do that? Okay, here's my explanation. That's a plausible explanation. Is, let's say, it's the difference between wholesale and retail, right? If you're buying small quantities, these weights are for that, and these are when you buy very large quantities, right? So somehow the system is changing. Okay, so now my question is, why would you go and represent weights in binary? All right, why would you do that? Why not do it in some other way? Okay, all right. So here is where combinatorial optimization comes in. So imagine a society, right, in which trade is happening, people are going to shops and they are buying stuff, and trade is happening. Now, the weights that you have are very important, right? They have to be issued by a central authority and maintained by a central authority, right? Because a shopkeeper may take a weight and chip it off to cheat customers and all that, right? So, yeah. बिल्कुल
सर मतलब ये 14 and like 14 can't it be combined using 2, 4 and 8? Why did they introduce a new symbol for 4?
हाँ, वो मेरी जो इसमें explanation है. Look, this is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 weights which are doubling. Okay, मेरी explanation ये है कि ये वाली जो weights हैं, these are being used in go downs for wholesale and things like that. All right, and these are probably used in the market. Okay, so they just did a different system for that. All right, okay. You're absolutely right that if they wanted to be perfect, this should have been a 16 here.
No, right. I'm saying that the last 3 symbols, if they are put in a sequence in binary, then they will won't they add up to 14?
Yeah. So the pattern breaks after this. Yeah, the pattern is breaking after this, right? And so my explanation of that is probably these were being used in the market, and those were being used by when there was some large-scale trading happening. So probably these weights weren't there with those people. Yeah, it's not perfect, right? Okay. All right. So the question, I was coming to combinatorial optimization. So if you are going to have this system in which you have a standardized way of making weights and then distributing them and then maintaining them, then what would you want to do? You would want to have the smallest number of weights. Okay? The fewer the weights, the better it is. Right? Because the authority will go, let's say they go and come to inspection to a shop to check their weights. If there are fewer weights, they'll be able to check them quickly. Right? Okay? Okay. So the combinatorial optimization problem is this one. So what we want to do is we want to weigh all weights, all masses, okay, of say 1, 2, 3, 4, 5, all the way up to n. Okay, and your task is to design the smallest weight set that can accomplish this. Okay, all right. And why would we want the smallest weight set? Because it will make our job easier of producing them and maintaining them, right? Okay, so or you could ask the question in a slightly different way. You can turn it around and you say, design a set of k weights so that all masses of size, the weight is a very busy word here, of 1, 2, 3 up to n can be measured. Okay, but here your task is to maximize n. Okay, be able to weigh as much as possible. Okay, so this is the same question, right? There's a minimization question, the other is a maximization question. Can we move this? Yeah, I guess I can. Okay. All right. Okay. All right. Okay. So if you were to have one weight allowed, if k was 1, what would be the weight that you will make?
Smallest.
Yeah, we don't have a choice, right? So with one weight, you will make 1, right? Now if I say you are allowed to have 2 weights, then what would be the next one that you would pick? Okay, you will have to pick 2, right? Because you have to be able to weigh 1 and 2. But 3 comes for free, right? What you can do is, here's 1, right? Okay, and here's 2, put them together and you have 3, right? Okay, so 3 comes for free. So what would be the next weight that you would pick? Yes, 4, okay. All right, so you get 4, you get 5, 4 plus 1 is 5, and you get 6, 4 plus 2 is 6, and you get 7, okay. So the next one you would go is 8, right? Okay, and after 8 you get 8 plus 1, 9 for free, 8 plus 2, 10 for free, 8 plus 2 plus 1, 11 for free, 8 plus 4, 12 for free, 8 plus 1 plus 4, 13 for free, 14 and 15 for free. So what's the next one you take? Okay, you would take 16. All right. Okay, now let me ask you. I will show you that this is the best possible. You cannot do better. Okay, I'll prove that for you. But tell me, is this the best? I mean, did they actually find out the optimal method for doing this? Is this the optimal? Okay, and the answer is yes and no. Okay, and I love mathematics. People think that in mathematics all the answers are very straightforward, yes or no, but not both. But they can be yes and no, and this is with an explanation. Okay, all right, so let me try to be a bit clever. So the first weight that I may get is 1, all right? And then what I do is the second weight is not 2, but it's 3. Okay? Okay, so how do I weigh 2? Well, I can by doing this, right? Okay? By subtracting. So if I allow myself subtraction, then 2 is not the optimal one. Okay? Actually, I have to tell you this story. I went yesterday for 2 hours in Lahore looking for a balance. मुझे तराजू okay, and I couldn't find one. Okay, everywhere I went, they had this spring one, which had either that one or electronic ones. They told me to go to Purana Lahore, which is not possible for me. I can't drive there, so they aren't available. Otherwise, I would have brought. So if you take 1 and 3, right, then the way you get 1 is 1. The way you get 3 is 3 minus 1. Okay, yeah, sorry, 2. And then the way you get 3 is 3. So what would be the next weight you will put? 9. Okay, what will be the next weight you will put? Yeah, well, Akmal got it. It's 9, and okay, because how will you get 4? 4 is 3 plus 1. Okay, how would you get 5? Is 9 minus 3 minus 1, right? That's 5, okay? And to get 6, it's 9 minus 3. To get 7 is? 9. Right. And then after that?
9 minus 1. 9 minus 1.
Plus 3 minus 1?
9 minus 1, 8.
Minus 1.
Oh, 9 minus 1, 8, yeah, okay. And then you get 9. And then after 9, you could get 9 plus 1 and so on. You will get all the way up to 1 plus 3 plus 9 is 13. It's 13, right? Okay. So what will, not you. Okay. What will be the next weight you will put? Oh, come on now. Huh?
27.
Yeah, it's 27. And of course, you realize that 27 minus 9 minus 3 minus 1 is how much?
14.
14, right? So these were taking you to 13, and you get 14 from here, and then you can get 15 up to all the way up to 27, and then you get 27, and then keep adding, and you'll go up to, I think you go up to 40 or something like that, right? So this is the most efficient one, and I will actually give you a proof of this in a little while. But tell me, why didn't the Indus Valley people go for this? And I believe they were smart enough. Okay, they just
Balance karna padta hai because fractions are difficult.
Yeah, you'll drive, even if you could train the shopkeepers, you'll drive the customers crazy. It'll be very difficult to convince a customer that, you have place the weights properly. So, yeah. It doesn't seem socially possible. I mean, I think it will be, probably this system probably, even in today would not work. You know, customers will get, you know, at that time, education wasn't that, right? So, okay, all right, so, now, let's do something. Okay, let me do a little bit for you. Okay. So if I have weights, okay. All right. So this is 3 to the 0. This is 3 to the 1. This is 3 to the 2. Okay, and all the way up to this is 3 to the k minus 1. There are k weights because we are starting to count from 0, right? There's a 3 to the 0 there. So they are k weights. So it's pretty funny. Computer scientists always start counting from 0. Okay, and there's this joke about a computer scientist who was at the airport, he was counting his children. 0, 1, 2, 3. Where's the fourth one? Where's the fourth one? So we are used to counting from there. Now, if I have these weights, then I will be able to weigh everything up to 1 plus 3 squared up to 3 to the k minus 1, right? Okay, that would be the largest weight I'll be able to weigh. Let's call this sum S, and let's try to figure out, you know, how this, what does this add to? You know, you people are familiar with this trick, but I'll do it nonetheless. Let's multiply this by 3, and we get something very similar, which is we get 3 plus 3 squared plus 3 cubed plus up to 3 to the k, right? And let's subtract this from it, okay? And so what happens is all the terms start cancelling. So this 3 cancels here, 3 squared cancels here. Everything cancels, and what you're left with is just these two things. Okay, so this is 3 to the k minus 1. Okay, but this was 3s minus s. So this was actually 2 times s. So s is 3 to the k minus 1 over 2, right? Okay, that's how much we can weigh up to. Okay, now, is it possible to do better? Maybe there's a bizarre way of choosing weights which can do one better than this. Okay, so that's the question. So what happens in mathematics is once you find a solution, you just don't say this is the best. You have to give a reason. You have to prove that it's the best. Okay, all right. So any ideas on how will we go about doing that?
By going to 5?
By? Huh? By 5 meaning?
Powers of 5.
Powers of 5? Ah. Oh, so you're saying you are going to come up with a new system which will have powers of 5.
Yes.
Powers of 5, the problem is if I take 1 and I take 5, I can weigh 1, I can weigh 4, I can weigh 5 and 6. But what about 2 and 3? There's a gap. So that solution is not acceptable. You remember? We want to be able to weigh everything in between also.
Yes,
You know, otherwise you'll just take very large weight. Okay, but that's cheating, you know.
This is the best we can do.
Okay.
Because you have only addition and subtraction. If you're not allowed any more operations, so if you only had addition, you could go from 1 to 2. If you added subtraction to the mix, then you could go from 3 to 2. But you can use addition or subtraction to go from 4 to 2. You'll have to use division or something else.
Yeah. So your argument is correct. Let me just lay it down properly. Okay. So there are two things that I want to convince you of is that it's always possible to weigh 0. Right? Just don't put anything. Right? So that's the proof that you can weigh 0. The other thing is that if you can weigh Okay, so this is actually 8, 9 minus 3. If you can weigh a weight A, then by doing this, what are you doing? Okay. You're weighing the same thing, all right? In this one, you're going to put the goods on this side. Okay. In this one, you're going to put the goods on that side. So there are actually two ways of weighing every positive thing. Okay, right? Just transform all the weights from this to this, and you're weighing it either in the left pan or in the right pan. Okay, all right. Now, when you have a weight, you have only three choices. That three things you can do with it. You have two pans. You can either put it in the left pan, or you can put it in the right pan, or you can not put any. Okay? In other words, the coefficient you can give to any weight is either 0, +1, or -1. Okay? So the coefficient you can give to a weight is, so we have, okay. Okay, so for every weight, I have three possibilities. Either give its coefficient 0 or +1 or -1. And so for all weights, how many possibilities I have? 3 for the first one, 3 for the second one, 3 for the third one, and so on, 3 for the kth one. So that will be 3 times 3 times 3. Okay, and this would be 3 to the k. Right? These are the total possible weighings I can do. Right? Ways I can place these weights. All right? Now they have to weigh distinct things from 1 to n, and they also weigh distinct things from -1 to n. You know, by that argument. Okay? So how many total things these are is 2n plus 1. Right? And each one of them has to correspond to one way of placing weights. So this quantity cannot exceed 3 to the k. All right? And so that tells me that n has to be less than 3 to the k. Exactly what we get here. Okay?
Can you repeat that? Why 2n plus 1 should be less than 3 to the k?
Okay. So if I place weights, it gives me a particular number. Right? If I place the same weight, same way, it will keep giving me the same number. Right? So every number, okay, must correspond to a way of placing weights. Okay? All right? So they cannot be, okay? Or in other words, every way of placing weights can give you one number. It cannot give you two numbers. And this is the total numbers you need. Okay, the way I got this 2 was with the symmetry argument, and the way I got 0 was by saying 0 has to be represented in any weighing system. You can weigh it by not putting anything. All right, so this has to be, all right. So that means that this is optimal. All right, you can use the same argument to show that the Mohenjo-daro way of doing things is also optimal. Over there, what you're saying is that the shopkeeper only places weights on one weight, right? They can't place it on the other one. So that means your coefficients can be 0 or 1, right? And you have k weights, right? So you have total 2 to the k possibilities, right? But there the symmetry argument doesn't come into play, you know, because the shopkeeper's weight is always fixed. So you either place or not place. So you have 2 to the k ways of doing it. Okay? And of course you can weigh 0. So you go from 0 to n. So that tells you that n plus 1 has to be less than this. And so n has to be less than 2 to the k minus 1. Okay? All right? And of course with the I forgot to do one thing, and that's just to show you, and I think you people are all experts at doing this. So if you take k weights, this is the largest you can be, right? So let's call this sum S, and let's compute 2 times S. That will be 2 plus 2 squared plus. Okay, and let's subtract this from here. All minus signs. So you will have a 2 to the k minus 1 left here. Everything else will cancel. Right? Okay. So that's saying that they also had their optimal thing because they weren't allowing the shopkeepers to place weights on 2 sides. All right? So, I actually find this this fascinating that and I also I know that when binary number systems are taught to students, it'd be very nice if we could tell a little story behind it, right? And this story is our story in some sense, right? So I'm not a big fan of thumping your chest and saying we were so great in the past. That's, I think, is a very bad attitude. I think the right attitude is to marvel at our ancient people and say, if they could do such great things, why can't we? Why can't we do it now also? So, this would be a very inspiring way of introducing the binary system to our children over here, and also introducing them to a little bit of archaeology and their, generating some interest in that field also. Okay, so shall we stop here? I can take some questions at the end.
So what was the value of K that the Indus Valley people were using? How many weights of 2 were they using?
So
up till 16?
1/8 to 6.
1/8 to
1/8 to 8. Okay, so let's just count them. It was, wait. I have to use my chalk. Okay, 1/8, 1/4, 1/2, 1, 2, 4, 8. So this is 1, 2, 3, 4, 5, 6, 7.
2 to the power 7
Two
minus
to-
1.
Yeah.
That was the maximum weight they could measure using these units.
Yeah.
To the power 7.
Yeah,
What's
if
that?
you take 1/8 to be the
127.
Yeah, if you take 1/8 to be the unit, right? 1/8 to be the unit, yeah. Yeah, it's pretty interesting if you go to goldsmiths, right? They are measuring things in ratti and masha and tola and things like that. Even I've heard nowadays they. अच्छा आजकल ग्राम से ही करते हैं, लेकिन if you look at
हमारे बचपन में हम 1 आना, 2 आना, उनके सिक्के, फिर
4
54, 58 और फिर रुपया होता है।
राइट, और रुपए में 16 आने होते
लेकिन रुपए के बाद फिर ये सिलसिला रुक जाता है ना। उसके पैसा तो फिर बाद में आया। अगर नीचे जाएं तो उधर भी नहीं था। उधर 1 पाई थी और हाँ।
So people
लेकिन देखिए उससे नीचे नहीं और उससे ऊपर नहीं, तो बस ये रुपए के लिए था उसके
डबलिंग। Yeah.
सुधार बहुत अरसे तक इस्तेमाल।
Yeah, Tola Masharati, they are powers of 2 of each other. In fact, I think कि आना भी वो यूज करते हैं at some point. करते थे हाँ।
आना तो सिक्के
नहीं, as a weight, yeah, as a weight, yeah.
This is very interesting as far as weight is concerned. But there is another way of looking at what about counting? Because you jump to weighing things, but if you go into a case for tertiary system or decimal system, I was reading it somewhere that why there are civilizations who actually use, instead of decimal system, I think 35 base system. And the reason is that because they have some astronomical numbers. Because when you're dealing with large quantities, then binary is a disadvantage. So it's an interesting thing that, weighing, I never thought about weighing things in that way. There's clearly a strong case for binary, but you can't go with large numbers because then it becomes problematic to record those numbers.
Yeah. So yes, okay. There are other bases that we use, and they were in practice. The one particular one that I know about is the Egyptian number system, which was base 60, right?
Mayans use 35.
Yeah. So for example, 60 is still used in our watches, right? There's 60 seconds in a minute, 60 minutes in an hour. There is a reason why they did that. The reason was they didn't discover zero. Okay, so they didn't have zero. So what used to happen is people used to guess the number from the context. Okay, now if you're going to, so if I tell you that I'm going to send you 3 goats, right? So the zeros would be like optional. Okay, so you were supposed to guess whether I'm going to send you 3 or 30. So smaller base, there's a chance of confusion. So having a very large base allowed them to, represent.
Recording large number, again, the larger systems has advantage.
Yes, but the advantage is very slight because, so if you have unary, right, that's useless. As soon as you go to binary, the length of the number is actually log to the base b if you want to represent the number n. All right, so once b reaches a certain place, it's not really worth it because the log function then stays more or less the same, right? So this would be the length. So I think the large bases were because there was no zero to avoid ambiguity. That's what my.
Also the factorization part, isn't it? 60 is the largest number of factors.
Yeah, 60 is, 6 is a perfect number. Yeah, it has a lot of divisors. Yeah, that is also a very major consideration. People wanted to have numbers which have a lot of divisors, right? So because that helps ease calculations.
It's probably also this days in the month, number of days in the month.
Yes.
Sort of roughly 30, so that may happen also.
Yes.
Partly.
So for example, 12 is something which is also
12
there.
months in a year.
12 months in a year,
30 days in a month.
we buy eggs in dozens, right?
Yeah, so
Okay.
physical.
Yeah.
My question was, you assumed that this was from left to right.
Yes.
Why?
Oh, okay. I think that their script was written this way, in this direction, right to left, and people can prove this to you, right? What they do is they just analyze seals, and by the way, there's a negative seal and there's a positive seal, right? So what happens is somebody is writing, and then these things get crunched in, as if somebody was writing and they ran out of space. And in some cases, they will start writing, and here they'll put one character here, as if there was no room for it there. Okay, all right. So if I'm starting to write something here, as my room runs out, I'll start compressing my letters, right? So by looking at that, they can tell the direction of writing.
It can happen both ways. I mean, if you have
No, so
that which way you write, I mean,
no, if I'm
you run out of space both ways.
Oh, no. Abdullah, let's say this is paper, right?
Yeah.
And I start writing here. I decide where I'm going to start from. So when I'm going to run out of space is on this side, right? I'm never on this side.
Yeah, basically, all the seals that they found, they analyzed them and
Yeah. Yeah.
And
So
the
let
only
me
place
let me
where
do this.
the
I'm writing
words were
A,
crunched.
and then I run out of space. Okay, so either I'll tend to compress this side,
Yeah, so
but
this
not
is-
this side.
Yeah, so
Yeah.
this is from the archaeological
Yeah,
evidence.
yeah. This they can they can prove statistically also that what is the direction, right?
Or it may be a stupid question. Lekin binary, one advantage of binary is that you have to deal with only one symbol, two symbols, 0 and 1. Why having so many fishes then? Fish like F0, F1, F2, F3? Because then the place is signifying.
Yeah. So what you're saying is that in some sense their solution is not optimal because they didn't just say that the presence of a fish would be 1 and the absence of a fish would be
No fish, no number.
yeah. I don't know why they didn't think of that. Probably if they would have thought of that, they would have
I think probably yes.
just understood the binary.
I think they were using multiple fishes because they didn't have 0, and different fishes signified presence of that fish
Oh,
and its placeholder.
Yeah,
So
yeah.
it was combined.
Yeah.
information.
He's got the thing. Look, 0 was discovered very late in mathematics. It's perhaps one of the hardest inventions that mathematicians came up with, right? So it's in the Bakshali manuscript, right? Which is how old?
Yeah, it was a few hundred CE.
Few hundred CE. So these.
But I didn't make. Why for 0 you need different symbols?
नहीं, 0 के लिए symbol बनाना, this shuni, this symbol, this was one of the greatest invention of mathematics.
Right.
You know-
Especially when you are subtracting. Otherwise, if you are just weighing, so
Yeah.
you're weighing nothing. There's no need to invent
Yeah.
0 if you are just weighing.
Yeah, so ये तो बख्शली manuscript तक नहीं
Right.
human.
I'm just trying to relate these two things. That why do we need different symbols in binary system if
If
if you don't have 0,
if you cannot even conceive of 0,
right?
right? Then the way you write something is you write the placeholder for it, its presence, and if you don't write it, its absence.
Right. So then why do we need different symbols for fish? That was my question. That you can have one symbol and omission, or you can.
They don't have the
That
concept of
would
zero.
be a confusion if the extra space is accidental or intentional.
No, but the blank space, like in computer, you treat blank space as a symbol.
Yeah,
when you conceive.
Tur, I think that, let me tell you, the blank space being a placeholder was a very late invention in mathematics. Okay, वो डॉट डालते थे जो accountants थे ना, Indian accountants, they used to put a dot there that, oh, there is something missing here. That became then later on 0. So conceptually, having a placeholder where you don't put anything is a
But I'm saying that instead of having F0, F1, F2, all the way up to Fn, just assign one symbol, say F3 for placeholder. Why using all those symbols?
Okay, so suppose I have F3 and here I want to write F0, F3, F5. तो इसको आप कैसे propose कर?
F3 means, just assign a symbol for placeholder. Rather than so many symbols, you go all the way.
Okay.
One advantage in binary is that you have to deal with only two.
Okay, so you're saying that this is how you would write it. You would write F3, एक ही symbol होगा, इसको F ही कर देते हैं ना, 3 पे क्यों करें? ठीक है? 2 missing है तो आप कुछ नहीं लिखेंगे, फिर आप 3 लिखेंगे, फिर वही F लिखेंगे, फिर आप 4 missing है, फिर 5. ये कह रहे हैं ना आप? When you're saying this, you're saying invent a 0. This is your 0. Okay? And when you're saying invent a 0, you're telling...
In the process, you end up inventing so many other symbols.
Yeah, you're telling those ancients to move few thousand years ahead. It took mathematicians thousands of years to invent this 0. And the way it was invented was they used to put a dot here. ताकि पता चले कि यहाँ पे एक चीज़ missing है. वो invention बहुत आगे आती है. This is as Abdullah said, right? 300,
Few hundred, I don't know exactly.
300 or 400 years CE. What is it? BCE, BCE.
No, not
CE, common era.
after.
अच्छा अच्छा
It's the current era.
ठीक ठीक
आपने वहाँ वो चार्ट दिखाए थे कि छोटी डिनोमिनेशन के लिए तो फैक्टर ऑफ 2 से बदलती है और ग्रो या थोक की मार्केट के लिए वो नहीं बदलती।
That's my thing. हाँ.
लेकिन उसमें वो 14 का एक सिंबल था और 20 का भी था, तो हाउ मच फिश डेटा, हाउ मेनी seals, how much data is there to derive this kind of information, precise information कि ये चीज़ 20 के लिए थी या 40, but how much data exists out there?
Okay, so there is a website called harappa.com, and that's where these people share a lot of their data, and you can find many things.
उस पर लिखा हुआ भी था स्लाइड पे ना, फ्रीक्वेंसी का भी एक कॉलम था, कितनी सील्स मिली हैं इस वाले फिश के सिंबल के साथ।
So they have that data. It must be in thousands. The other thing is data is being constantly added. जैसे ये जो राखीगिरी है, उसकी साइट हरियाणा में मिली है, which is bigger than Mohenjo-daro.
Use the same script.
Yeah, it's Indus Valley. And I have seen some of their papers when I read it. They're very detailed. उसमें एक घर का मैप होगा और उसमें लिखा होगा कि कौन सी सील कौन से कमरे में से किस जगह से मिली है. So they have that kind of detail. It's really fascinating. There are seals जिसमें एक तरफ Indus Valley की स्क्रिप्ट है और दूसरी तरफ Mesopotamian seal है. And they think it's like some kind of a passport or a contract for traders to use and all that.
Rosetta Stone,
They haven't found the Rosetta Stone. If they find,
or Indus Valley.
yeah, that would be like a dream come true. I would really love to listen to their poetry, okay? Because language is about poetry. Do you guys know that even in sign language there is poetry? And
It's so frustrating that we know so little about them. Like there is no written records.
yeah,
That's like whenever I googled about it, there is so little that has. They have no,
They have no voice.
written language as such.
Yeah, they
These seals were just for the cargo.
yeah. I have concentrated on the fish sign, but people can categorize कि यहाँ weight लिखा है, यहाँ बंदे का नाम लिखा है, यहाँ family है, and they can do that, but they can't really read it properly. There is one or two banners that they have found, which don't have fish sign or anything. So it might be like a welcome to a city or something. Okay, that would be interesting to decipher. How did
There's
they?
also some historians are of the opinion that they might be a peaceful society,
People
a utopian peaceful society. Others disagree. Yeah.
Well, it was very egalitarian. There are no palaces, there are no pyramids, there are no huge temples, right? Some people claim, people go as far as saying it was the first democracy. There's no. Huh?
Weapons.
They haven't found very many weapons, I think.
Weapons were a little blunt. Actually, yesterday I happened to be watching a YouTube. So there are arrows, but they are too blunt to probably kill a person.
So
To be used as a weapon.
So-
they're more like kitchen.
What for hunting? No hunting?
they seem like agricultural people, but
Or fishermen, maybe.
yeah. But I remember when I met Paul Erdős. He's one of the greatest mathematicians of last century. As soon as he heard that I'm from Pakistan, he started asking me about Mohenjo-daro, and he kept on asking me things. So he said, what happened to these people? How did they, vanish? So I said that one of the theories is that the Aryans came from the north and essentially overran them. So he said, if they were so civilized, didn't they have weapons to protect themselves? I said, the reason they didn't have any weapons is because they were civilized, Paul. and he had this huge smile. He approved of me so much. It was a lovely moment of my life. So there's also a story of Buddha, that there were two cities. One was democratic and egalitarian, and another one people just used violence at every every dispute was settled with violence or whatever. So this violent people overran this city, and when Buddha was told the news, they say that Buddha frowned. Okay, and they said he frowned very few times in his life. So anyway, let's hope we can be like the way we idealize these people.